Okay, so we continue our discussion of projectile motion, and last time we focused only on vertical launches. And of course, I just started off with an example here reminding us of how to do that, where we're standing at the base of a 15-meter building. We're going to toss a ball upward at 21 meters per second, and our friend standing on top of the building is going to catch it. And the question is, how long after we throw it will our friend catch it on top of the building? And so, of course, we're going to use our three-step approach. We're going to draw the situation. We're going to clearly designate positive directions, which I'm going to go with down as positive. And, I told you last time that that's because I like to keep the acceleration positive, even though most people like up being positive. I always want the acceleration to be positive. And so I'm going to choose down as positive. And I'm going to list out the given information, which in this case, because the ball is going to land higher than it starts, it's going to be in a more negative position, so the change in y is going to be negative 15 meters. The initial velocity is up, and since I've chosen down as positive, that makes that negative 21 meters per second, and the acceleration is positive 10 meters per second squared, because in the absence of air resistance, the acceleration is only due to the gravitational field of the Earth. Now, you could reverse all of these signs, right? You could choose up as positive and make the 15 and 21 positive and the 10 negative. You'll get the exact same answer. I'm just trying to get you in the habit of making acceleration positive for later problems where it's more problematic. But either way, you'll have this information, and of course I can put it into my kinematics equation for delta y, and rearrange and get it into standard form. I will warn you on this, the most common error in this algebra is, if you notice, the negative 15 on the left, when I move it over to the right, becomes positive, and so a lot of students mess that up. So just watch your signs as you rearrange. Get it in standard form, use your quadratic equation solver, and you'll get two roots. The first root is 0.91, the other is 3.3, and this is different than the ones we worked before because both roots are positive. And you say, well, which one do I keep? Well, it depends on what the question's asking, right? Keep in mind what the math means. This is a function of the position as a function of time, and so it's telling us, the roots are telling us when it's at the height of 15 meters. And so as you can see from the picture, that happens twice. The ball will be at the roof height once on the way up. Then it'll reach its peak and return to the ball height later. And so that's what these two roots are, and that's why they're both positive. After I toss it, I'll have, it'll be at roof height at 0.91 and be back down at roof height at 3.3. And of course, the way I ask this question, the answer is 3.3. But I also like to ask questions like, if my friend can't see it until it reaches roof height, how long will they have to adjust and get under the ball and catch it? And of course, then in that case, you would take the difference of those two roots, because that's how long it takes for it to go from roof height on the way up to roof height on the way down. All right, so that was just a review, and then we turned our attention to two-dimensional motion, so projectile launched horizontally. And these get a little bit more interesting. And the first thing we did was we did a demonstration in class where we launched a ball horizontally and dropped a ball at the same time. And for most people, surprisingly, they hit the ground at the same time. That is a little counterintuitive. I mentioned that Mythbusters did an episode several years ago where they fired a bullet horizontally and dropped one and showed how they will hit the ground at the same time. It's really unexpected. It's kind of fun. But mathematically, it makes perfect sense, because a ball dropped and a ball launched horizontally both have the same initial vertical velocity. 16 meters per second is only to the right, and so none of that is vertical. So the initial vertical velocity is 0. They have the same vertical acceleration because they're being pulled on by the same gravitational force of the Earth, and they're going to fall the same vertical distance. Sure, the ball launched horizontally goes farther, but vertically it ends up changing height the same. And so using that same kinematics equation we've been using, if the acceleration's the same, the initial velocity is the same, and the displacement's the same, then the time has to be the same. And so Again, that's a little counterintuitive, a little surprising, but makes sense math. All right, so now how do we solve a problem like this? Well, we're still going to do the same 3 steps. We've drawn it. You'll notice we don't have any vectors that are in both directions still. We have 15 meters in the y direction. We have delta x in the x direction, 16 meters per second in the x direction. And of course, the only acceleration is vertical. And so nobody is in both x and y, and so there's no vectors that we need to resolve. We do want to be careful of the positive direction as we list our given information. And I'm going to choose down as positive. And again, this makes a little bit more sense to most people because both the displacement and acceleration are positive. But again, you could work it with up as positive and you'd still get the right answer. Then I'm going to label all the given information because we're going to find time from the direction we know the most about. And so if I look at what I know here, I know that the change in y is going to be 15 meters down, and I'm calling down positive, so that's a positive number. I know that initially the ball is only moving to the right, and so it has an initial velocity of positive 16 meters per second in the x direction, but in the vertical direction, it has an initial velocity of 0. And then, of course, acceleration is in the down direction of 10 meters per second squared, so that's only vertical in what I've designated as the positive direction, and there's no acceleration in the x direction. And so this is, I put it in green because this is going to be true of all the projectile problems you work in this class. We might talk conceptually about what it means when you have air resistance, but everything we do as far as solving problems, we're going to ignore air resistance, and so the acceleration in the x direction is always going to be 0, and the acceleration in the y direction is always going to be 10 meters per second squared towards the center of planet Earth, which of course normal people call down. So that's going to be true for all these problems. All right, so now which direction do we know the most about? We're looking for delta x, and so we know more about delta y, so we start with that direction, and we use that direction to find the time. And then after that, we'll find what they told us to find. So I plug into delta y. I know that the initial vertical velocity is 0, so that term goes away, and I'm left with 1/2 at squared. Rearranging and solving, I get a time of 1.7 seconds. Now notice a couple of things here. First of all, notice that I haven't used the horizontal velocity at all. So the time it takes to hit the ground does not depend on the horizontal velocity. Excuse me. Also notice that I ended up with delta y equals 1/2 at squared, but I didn't start with that. Some students like to use shortcuts, right? And so they always say delta y equals 1/2 gt squared, and you'll see that in some textbooks. I hate that because that's only true if the initial velocity is 0. So always start off with what's always true and then narrow it down based on the conditions that we have. All right, so now that we know that the time is 1.7 seconds, now we're to the easy part. We know that we're supposed to find the horizontal displacement, so we turn our attention to the horizontal direction. We plug into initial velocity times time plus 1/2 acceleration times time squared. The horizontal acceleration is 0, so that term goes away, and it just ends up being 16 times 1.7, or 27 meters. And so the displacement, it's going to land 27 meters to the right of the base of the cliff. All right. And then I just said, I could have a follow-up question. I could ask, how fast is it going when it hits the ground? Well, first of all, when it's just about to hit the ground, let's say it's 5 meters off of the ground. When it's still 5 meters high, how fast is it going horizontally? Well, of course, it's going 16 meters per second because there's no horizontal acceleration. So the horizontal velocity is going to stay 16 the entire time. So then all that's left to find out how fast it's going is I just need to know how fast it's going vertically. And I can use that. I can find that by using this equation. The velocity now is the initial velocity plus acceleration times the time. If I focus on just the vertical direction, because I know the horizontal is not changing, then I can say right before it hits the ground, it's been 1.7 seconds. And so the vertical velocity will end up being 17 meters per second. And so I know the components of the velocity are 17 meters per second down and 16 meters per second to the right. I could just put those back together, right, to find the total velocity. So that's just an extension problem that I could have done here and just chose not to for the sake of time. All right, so then we worked this one, and I encourage you to pause and try and work this one on your own. It's very similar to the last one, and so it should be pretty straightforward, but go ahead. All right, so basically, same process. We're going to identify what we have, being careful about the positive directions. I know that the initial velocity is 11 meters per second to the right, and not at all up and down, so the initial vertical velocity is 0. I know it's going to fall 41 meters, so that's my change in y. I know more about y, so I'm going to focus on that to find the time, plug in there, and do algebra, and I get a time of 2.86 seconds. Then I can turn my attention to the horizontal direction. The acceleration is 0 in that direction, and so I plug in the velocity and the time to find the displacement. All right, so then now it really gets interesting. Oh, wait, sorry, just kidding. I forgot about this problem. This is very similar, but has a little bit of a twist. So go ahead and take a swing at this. All right, so again, same process. Identify positive directions and identify what we know. And what's different this time? Well, what's different this time is that we know more about the horizontal direction. And so when we go to find time, we're going to use the horizontal first. So I plug into horizontal, and that lets me find that the time is 2 seconds. And now I turn my attention to the other direction to find the vertical distance, which, of course, ends up being 20 meters. So again, this is exactly the same overall process. I just reverse the order of what you know and what you find. All right, now we get to the really interesting stuff. So now, what if we're going to launch at an angle? And this is kind of a classic projectile question, right? If I launch at 15 meters per second at a 40-degree angle, how far away will it land? All right. And by the way, I should say here, I gave my little speech about because I said so. Basically, you know, how many of your parents have ever said that to you, right? You say why, and they say because I said so. Well, I say because they said so on problems like this. Don't worry about how it got to 15 meters per second. Don't worry if they kicked it, they launched it, they threw it. It doesn't matter. This problem starts with the ball is launched 15 meters per second at a 40-degree angle. Why? Because they said so. Right? Never try and predict or guess or answer any questions about what happened before the question. A lot of students get hung up on that. You know, well, why is it moving 15 meters per second? They kick it, they throw it. It doesn't matter. They said so. All right? All right, but what that means is if you're 15 meters per second at a 40-degree angle, that means you're actually moving to the right and up at the same time. And so just like we've been doing all year, we're going to resolve that vector into components and say that 15 meters per second at 40 degrees is the same as 11.5 meters per second to the right at the same time you're going 9.6 meters per second up. And I advise students to go ahead and cross out that 15 because we're not going to use it anymore. We're replacing it with its components. And you don't want to accidentally multiply by 15 later when you're not supposed to. All right, so now it becomes just like the last problem, only just a little bit different algebra. We know that the initial vertical velocity is 9.6 up, and since I've chosen down as positive, I'm going to make that negative. The acceleration in the y direction is 10 meters per second squared in the down direction. And then notice it starts on the ground and ends on the ground, and so the overall change in y is going to be 0. And then, of course, I know the horizontal velocity is 11.5 meters per second to the right, and the acceleration in the horizontal direction, of course, is 0. So I know more about delta y, so I plug into that. And then here's just the only tricky part, right? If I have this algebra, 5t squared minus 9.6t, then I can't divide by a t. That would violate algebra. But I can factor it out. And when I factor it out, I get t times 5t minus 9.6 equals 0. Well, how can that expression on the right equal 0? Well, there's two ways. One, either the time equals 0 itself, right? T equals 0, and what's in parentheses is not 0. Or t does not equal 0, and what's in parentheses does equal 0. One of those two has to be 0. And so the two roots are either 0 or what's in that circle is 0. And so I take what's in that circle and set it equal to 0 and solve for t, and that gives me the second time of 1.92 seconds. And again, this is physically it makes sense because at first, when time equals 0, the ball is at ground height, and then 1.9 seconds later, it's going to be back at ground height. And so those are the two roots and the meaning of it, and so we're interested in the second one, the 1.92 seconds, and so we're going to use that root. All right, so if it's going to land 1.92 seconds later, now I turn my attention to the horizontal direction and plug into the horizontal equation where the acceleration is 0. And of course, then it means it travels 22 meters in that time. All right, so now take this one, 15 meters per second, but this time at a 50-degree angle. Take a minute and try and solve that on your own. Again, same process, break it down into the components, identify what the given information is. I know more about the y direction, so I use that to find the time. Again, the exact same algebra, 2.3 seconds. Plug that into the horizontal direction, and notice I get the exact same number. That might be surprising, right? And you might be asking yourself, well, does that mean that if I launch it at 15 meters per second, it's always going to go 22 meters? Well, of course, that doesn't make sense because if you launch it straight up, it's not going to go 22 meters. But what do you notice about the two angles I chose? The first one was 40 degrees, and this one's 50 degrees. Those are complementary. So think about what's going on. For the 50-degree angle, the component that was vertical was greater, and so the time in the air was longer. But for 40 degrees, the vertical component was smaller, so it wasn't in the air as long, but the horizontal component was greater, so it was moving faster to the right for the time it was in the air. And so anytime you have complementary angles, you're going to get the same horizontal displacement. And it also tells us something about how increasing the vertical component will increase the time, increasing the horizontal component will increase the speed to the right, and the combination of those two determines how far you go. And so basically, if you want to go the greatest horizontal distance, if you're going from ground to ground, you're going to launch at a 45-degree angle because that's going to help maximize both of those factors. Now, of course, if you go from a different height, it won't be 45, but from ground to ground, the maximum height is 45. The maximum range comes when the angle is 45. All right, and then we just worked this problem where now we're going to launch off of up on a surface, a cliff or something. And the first thing I would note is that to finish our discussion before, because we're starting from a height, we're going to gain time, right? We're going to automatically be in the air longer because we're up higher. And so now the maximum angle is no longer 45, but it's going to be slightly less because we're gaining the advantage of extra time so we can afford to have a greater horizontal velocity. I won't ask you to calculate that maximum angle or anything, but I just want you to know conceptually that's why. All right, but then this is exactly like the previous questions, right? I'm going to identify, going to break down into components and identify the positive directions, and then I'm going to list out what I know. But this time, there's not any zeros except for the horizontal acceleration. So when I go to use the vertical, I get this guy, right, which is, of course, a quadratic equation. Just like we did, though, with our vertical launches like this, we can use the quadratic equation solver. We get our two roots. The negative 0.9 seconds is back in, the past. If the ball had started off at ground height before it got to the cliff height, that would have happened 0.9 seconds ago, but we can ignore that because we don't care about what happened before the problem. After it's launched, it's going to land 1.57 seconds later. So I just use the horizontal equation, and I find that it lands 14.8 meters away. All right, so again, be careful with your positive directions, follow these steps, and you'll be able to solve any projectile motion problem. But as always, don't just stick to the steps and kind of memorize how to do it. Think about what's going on and always understand what's going on with math.